Hello everybody, Greg is here. So first of all, thanks a lot for watching the previous video. So today I want to tell a little story about the work I did in my PhD, and it relates to platinum chemistry. But let's start from the history. So the first organometallic compound ever was synthesized and identified in the 19th century. And that was a big deal because prior to this work by Sayce, here's the guy, it was believed that there's completely separate worlds of organic and inorganic molecules. If you have an organic molecule made of carbons and hydrogens, it should not coexist in one matter with the inorganic, like dead compounds, like in this case it's platinum salt. However, he obtained a new compound and he was able to prove that it actually contains both organic and inorganic material in it. Besides this molecule being the first inorganic compound identified by a human, it's also a compound in which a double bonded species is connected to a transition metal. Back then, of course, they did not realize that, but with time, after we learned how chemistry works and how the molecules interact, it was again a very important thing, and actually such molecules are very important for different transformation in chemistry, for catalysis and a lot of other things. Of course, scientists try to prepare many different compounds of this type with double bonds, not only for carbon double bonds, with the whole periodic table. But the most, I guess, closest relative of carbon-carbon double bond, a carbon-silicon double bond. Yeah, silicon is just below carbon on the periodic table. So such compound with silicon-carbon double bond was not created until 2004. So it's like almost 200 years past. And this compound that was synthesized in the group that I did my PhD. So there was the first direct interaction between silicon-carbon double bond and the platinum. And the reason it took so much time is because those compounds are not stable. The silicon-carbon double bonded compounds, if you want to make them stable, they should be big, so they cannot approach each other and react with each other. And if it's big, then platinum cannot approach them as well. So that's why no one could do it. What was done in this work is that the silicon-carbon double bonded compound, which his name is a silane. So the silane was small enough to be approachable by a platinum complex, but it was on the other hand big enough to survive. However, it was surviving only at low temperatures. When you increase the temperature, it was dimerizing. So most of the products in this particular reaction was the product of dimerization, and only a small portion of this doubly bonded compound was trapped by platinum, and it was again a special platinum complex with only two phosphine ligands and one of them left, so platinum can interact. And anyway, it was a hard reaction. I think 20% is a bit optimistic. So when we try to reproduce this reaction, there was only tiny amounts of this compound formed, even much less than 20%, sometimes 1%. This compound was isolated, synthesized. It was published because it was a breakthrough, first time direct interaction between double bond of silicon and carbon and the transition metal. However, no chemistry, no studies could have been done on this compound because it was just unreproducible. So a little bit later, I did something else. First of all, generated the same compound at higher temperature. So when you take this dimer and heat it to above 60 degrees, there is an equilibrium between the double bonded compound and the dimer. And also I took a platinum complex, which was a bit bigger on one hand, but it was also more stable, so it could survive at higher temperature. Well, this one, when you heat it, it decomposes. This one was more stable. And in my PhD work, I was able to synthesize quantitatively a platinum silane complex by doing this reaction. So that was the only product, and now you can do some stuff with it. Well, unfortunately, it was not a main topic of my research, so I kind of put it on the shelf and was dealing with other things. Maybe someone will keep doing that later. However, even just by synthesizing it, there was already several interesting things which we learned. I'll describe them in the next few slides. first interesting feature was the phosphorus NMR spectrum. So this compound, you see it has two phosphorus atoms, one in front of a carbon, one in front of silicon. So they're supposed to have different chemical shifts because they have different chemical environment. But if you look at the spectrum of the compound dissolved in hexane, you have only one peak, one central peak, and a few smaller ones. But if you dissolve it in benzene, then you see something that you would expect. You see two separate signals, each of them splits the other one because they have different chemical shifts. They're supposed to affect each other. I will not go into NMR theory, but let me know in the comments if you want me to make a separate video about how you investigate nuclear magnetic resonance signals. Anyway, so that's the spectrum you would expect, and that's what we saw in benzene. But in hexane, apparently both phosphorus atoms have similar chemical shifts, and the only way they different is by their interaction with platinum. Platinum has a magnetic isotope. A molecule contains platinum isotope, then the platinum will affect the NMR of phosphorus and it will split them. So in small number of molecules, you would get a doublet from platinum, and because each phosphorus interacts with platinum in a different way, you will get doublet of doublets. Same thing you have here. So when there is platinum isotope, yeah, you see two separate signals. But then there is no platinum magnetic isotope in the molecule, then you'll see only a singlet. So yeah, that's something you don't see very often, and we were lucky that we had spectra in two different solvents and we could understand what's going on. Of course, when you use different solvents, you have different chemical environment, and that makes changes in the nuclear magnetic resonance. I thought that maybe we can try to see how benzene interacts differently with platinum compared to hexane. This molecule here was crystallized from hexane. It was just a monomer. You don't see any solvent molecule here. So I tried to crystallize it out of benzene. And again, to another big surprise, we saw that one benzene molecule, here it is, here are its hydrogens here. So it makes a complex with 3 molecules of this platinum complex. Look at this. Such a beautiful structure, like 3 ships docking to some marine station. Of course, this is a solid state. We don't really know if that's exactly what's happening also in solution. Probably not, because these bonds here are very weak. First of all, they're very long. And if you take these crystals, dissolve them in hexane, and evaporate, you don't see this complex anymore. So benzene evaporates, it doesn't stay. However, I still believe you can get a different reactivity. There are actually many new publications, very, very recent ones, showing that those weak van der Waals forces, London forces, dispersion interactions, they sometimes have very, very strong effect on reactivity. So in this case, maybe the most interesting thing in the molecular structure is that the bond here between silicon and carbon, when it's the monomer crystallized from hexene, it's by 0.02 angstrom longer than when it's crystallized from benzene. Now one can say, well, it's only 0.2 angstrom, that's nothing. However, I disagree with this, because those tiny differences can be very important for reactivity differences. Likely the double bonded character of silicon carbon moiety here is a bit higher. Hope you liked this video, and I hope you learned something from it and it can be useful for your own research. Thanks for your attention. Please support Ukraine and the release of Israeli hostages from Hamas. Have a good day.